Recording in progress.
Yeah, comes on everyone. So last thing that we did was the flux part. Perfect. There. So last thing, just to brief it up, and this is what we have proved, that if you take a charge inside a closed surface, it doesn't matter what is the shape of the surface, the flux is q by epsilon. The charges outside will not contribute to any flux. That was the whole story there. Is this clear, everyone? All right, great. So let's see a question on this. We got a cube here. Of side A. You kept a charge q at the center. Phase 1, phase 2, phase 3, phase 4, phase 5, and phase 6. There are 6 phases. Find the flux through each phase. Others do keep your cams on. So there are 6 phases. So find the flux through each phase. So let's number them 1, 2, 3, 4, 5, and 6 is behind. Yeah. Get this one is an easy one. Okay, let's see. This is an easy one. So no. First thing, you kept a charge q inside of the cube. So direct story, right? The flux passing through the cube is simply q by epsilon. Like I said, it doesn't matter what kind of shape you take, it has to be q by epsilon. And then we will say, okay, by symmetry, if you see all 6 sides are looking identical, all 6 faces are symmetrical, therefore, flux through each face is q by 6 epsilon. Easy? Everyone got the logic? No. Let's build it up a little more. So the same cube, but this time I kept the charge in the corner. Find the flux through the cube and flux through each face. The center was easy. What if you had kept it at the corner? Now, what is the flux through the cube and what is the flux through each face? Now, what do you guys think? Now, you have to be careful. See, if you are inside, it is q by epsilon. If you're outside, it is 0. But if you are exactly on there, you have to be smart. So let's see how will you do that. Okay. What about the remaining faces, Samir? Right, Trishi. Utsa, exactly where? Yeah, get me flux through each face, each surface. Hmm. Think. I'll give another 30, 40 seconds, then I'll show you. Now, see, the thing is, if I know the charge is inside, then I can calculate the flux. So, what we will do, this cube which we got, so remember, this was the charge here, Q. Let's construct a cube, by adding, I'm changing the different colors. See, I will add 7 more cubes, right? So there are, 3 cubes at the bottom, and I'll keep another. Hmm, able to visualize this? So total ऐसा 8 cubes हो जाएगा. So add 7 more cubes. If you add 7 more cubes, now this whole thing will look like a big cube of side 2A, and your cube was here. And this point cube was in this corner. Does that make sense? No. So the flux through the big cube is q by epsilon. So that's the whole story there. If you are inside, it is q by epsilon. Now, since there are all cubes are identical, then the flux through the small cube should be 1/8. Any doubts on this? That was clear. So the corner of one cube will be the center of a bigger cube. हमने पहले भी किया था ऐसा कुछ लॉजिक, याद है कहाँ पे किया था? ये क्वेश्चन याद है? If the potential at point A is this, find the potential at this thing. Then we said to keep 7 more cubes, make a bigger cube. We did something similar. Question is still not over. We want the flux through each face. Right, Anvita. Right, Arya. Yeah, I think most of you did get it. Right, Srihari. So now look at the second part of it. Now look at this charge here. Because of this charge plus Q here, look at the field lines. The field lines will be parallel to the surface here. Can you observe here? So whichever surface the charge touches, if I put it on a flat surface, observe this thing. If we keep a charge Q here, the field lines will go parallel to the surface. That means the field lines and the area vector are perpendicular. Suppose if I keep it this way, the field lines will go parallel to the surface. The area vector will be this way, perpendicular. So surfaces which touch the charge, the flat surfaces, or which in contact with the charge, have field lines parallel to the surface. Therefore, E is perpendicular to A. Matlab, therefore, flux is 0. So in our question, so this is 1, 2, 3, 4, 5, and 6. You can clearly see 3 to 6 are touching. The flux through 3, 2, and 6 is 0. And you can clearly see flux due to 1 and 5 and 4, these three are identical. That should be 1/3 of the total flux. What is the total flux? Q by 8 epsilon. So that will be Q by 24 epsilon. Is that making sense? So the total cube will get only 1/8 of the flux. In that 1/8, only these three people, 1, 4, 5 will have flux. 3 to 6, they will not have any field lines crossing them. They'll just be parallel to the surface. So this surface, and there's a surface at the back also. And those three surfaces will have zero flux. All clear with this? Is this making sense? And this is what I said about the chapter. Like you will actually prove everything with arguments. Any doubts on this? Others, do adjust your cams. Make sure your faces are visible on the screen. Any doubts on this? Clear, na, Tanishka? Sure. Sudiksha? Yashvi? Clear? No. Same question. We will continue playing with this. So this charge Q here, which you kept, let's say it is moved slightly. This is your face center. So face ka center. So this charge Q is slightly moved here. You're getting it? So the plus Q is slightly moved on this surface, and these things are still same. So this is 1, this is 2, 3, 4, 5, and 6 is behind. If the charge plus Q is moved slightly, matlab very small, negligible almost, but it is moved slightly towards the face center of 2. Now find the flux on each face. It's not in the corner anymore. You pushed it little inside. Matlab, it's still on the surface. Phase 2 along the surface. You're sliding on the surface basically. Now what will be the flux through each face? So there are variations of this. What happens if you push the charge slightly towards the center, cube ka center, away from cube ka center? So there are all variations. So this is a good one. How will you handle this? Each face one. नहीं रे त्रिशी. I'll tell you one thing. Listen, since you moved it very little, if you ask phase 1, phase 4, and phase 5, if you ask them where is the charge, what will they say? They will say there it is still at the corner, right? For these three phases, if you ask them, boss, where do you think is the charge? They will say, we think the Q is still in the corner. So the field is same, the angle is same, everything else is same. Do you agree with that statement? Just because we are using this word slightly. If the phase 1, 4, and 5 think the charge is still at the corner, and if they think the field is same, if they think the angle is same, shouldn't they also think the flux is same? You guys agree with that statement? That means whatever you got in the previous question answer, q by 24 epsilon, this will remain same for 154. Are you clear with that argument? All this is happening because you just pushed it very little. If you pushed it a lot, this wouldn't have been true. Sure what I'm saying? So 145 will remain same as the previous question. That was the idea there. What about the remaining three? Now think from that perspective. Try. I'll give you a minute. It's a good one. You moved it such a small distance. 145 are so far, they will think, yaar, abhi bhi charge corner mein hai. That was the main theme in the question. You can't say that about 3 and 6 because for 3 and 6, the moment you push here, these field lines are not radial anymore. The field lines are coming at an angle. And the surfaces which are very close, we have a very high electric field. So there will be a flux. The field lines will start crossing them at an angle. So it won't work for 3, 6, and 2. नहीं समझा. Think. Everyone take another minute, 40 seconds, and then I'll show you. In the chair and on the face and not the corner. So QI2 is in the. That is true, Trishi. What you said was right. That was perfect. But what was that? That would give you the total flux in the cube, isn't it? Yeah. That argument was right. Param there. Yeah. Okay. Should I help you? So no. So the first argument is this. The faces 1, 4, 5 still think plus q is at the corner. Because it's very far for them, like since it moved very little. Therefore, flux through 1, 4, and 5 will still remain q by 24 epsilon. Perfect. Now, since you moved it on the diagonal, अभी देखो क्या होगा. If you construct one more cube like this, now for these two cubes, the charge is somewhere here, isn't it? That means each cube will get q by 2 epsilon, and this cube will get q by 2 epsilon. Do you agree with that? If you put one more cube on the right hand side, now this thing is inside, and the flux inside is q by epsilon. Since there are two cubes, it is q by 2 epsilon each. That means because of pushing this along the diagonal, you have changed the flux from q by 2 epsilon, q by 8 epsilon to q by 2 epsilon ho gaya. Is that making sense? That means the flux through phase 1 plus 2 plus 3, 4, 5, and 6, the sum must be q by 2 epsilon. And flux to 2 will be 0. Why? Because the charge is touching the surface. That statement we just now made it. Flux to is 0 since the charge is on the face. Charge is in contact with the surface. Perfect. And we can also say for this charge, if you ask it, boss, what do you think about 3 and 6? 3 and 6 are symmetrical. So if you look at this argument here, flux through 3 and flux through 6 is same. Because for the charge q, if you see when you move diagonal, 3 and 6 will look identical. Remember, 3 is the ceiling and 6 is the other that face. They're equal due to symmetry. Perfect. I think then you're done. So flux 145 is q by 24 epsilon. So that would be q by 8 epsilon plus 2 times flux through 3 is equal to q by 2 epsilon. That will give you flux and 3 surface will be 3q by 8 epsilon. 3q by 8, 16 epsilon. Check. Yeah. So did you see what happened? Just moving it slightly. Yeah, right, Arya. The flux suddenly went from 0 to 3q by 16 epsilon. The whole thing changed. The cube suddenly got from q by 8 to q by 2. Matlab flux became 4 times just because you moved it little. Like I said, what is again flux again? The number of lines crossing through an area. When you're in the corner, the three faces scale lines became parallel. But once you pushed it, suddenly the lines started crossing them. So yeah, it's a different thing. Is this clear, everyone? That this is how they can play around. Any doubts on this? All clear with this? Let's see something similar. So we got a cube here. Phase 1, 2, 3, 4, 5, and 6. We have an infinite line charge passing through one of the side. Infinite line charge lambda. Find the flux through each face. The side of the cube is L. Remember, there's only one concept I taught you. If the charge is inside, flux is q by epsilon. If the charge is outside, flux is 0. Bus. This is the only thing that you learned. All we are playing is symmetries. Give it a try. So how are we doing this? What is the flux through each face? Meaning they could have, done something like this. They could have kept one more line here. Two infinite line charges. They could play the game. The idea is the same. Find the flux through each face. Okay. Lambda by 8 epsilon. Which face रहे हो भैया? Total नहीं चाहिए मुझे. I want through each face. ना? There are 6 faces. Lambda by 12. नहीं रहे सम्यक. There will be 4 faces which will be 0. Remember the statement. If a face touches the charge, it will be 0. मतलब यहाँ पे if you observe, the lines will be parallel to phase 3, the lines will be parallel to phase 5, lines will be parallel to phase 1, lines will be parallel to phase 4. There are 4 faces touching the line charge. All 4 will be 0. If a flat surface touches the charge, done discussion, the lines will go parallel to that for a point charge. And infinite line charge is also symmetry. And I hope you remember how well the field lines will look for an infinite line charge. Let me show you that in case. This is how field lines will look for an infinite line charge. Now, what you're doing here is you're keeping a surface here. So these lines will come parallel to the surface, so there'll be no flux. Okay, let's see. So first thing, let's see how much is the cube contributing. So what I will do, I'll construct actually, I'll put three more cubes. I just need three more cubes only. I don't need eight cubes now. See, if I keep three more cubes like this, total four cubes, and my infinite line charge is passing through the four of them through the center like this. Can you see this thing? Four cubes are there. So inside this, how much charge is stuck? This is the charge which is stuck. I'm putting in dark. See. So this charge Q will be lambda into L. So the total flux through four cubes, it is inside now, lambda L by epsilon. So flux through each cube is lambda L by 4 epsilon. So because of the infinite line charge, you are getting only lambda L by 4 epsilon. Yeah, 13450, right over here. That is there. What about the rest? And now coming back to this argument here. So these four flat surfaces are touching the infinite line charge, which is 1, 2, 3, 4, 5, and 6. So flux through 1, 3, 4, and 5 is 0 because they're touching. The only guys left are flux 2 and 6. That should be half of the total flux because where else will it go? That would be lambda L by 8 epsilon. Nah, there is no center of charge concept. Is that clear, everyone? Lambda L by 8 epsilon. Right over here, you got it. Oh, you're typing the final answer. Right, Anita. Ishman got it. Yeah, most of you did get it. Shaurya, yeah, you got the total. Yeah. All clear with this? Making sense? How is the question? If you can see, right, it's all symmetries. मतलब आपको सिर्फ वो symmetries देखना था. Let's see one more. This is a JEE Advanced 2015 question. Let's see how will you handle this. Read the question. Everything that you need is there. I won't explain the question. Try for 2-3 minutes, then I'll show you. Okay, let's see. Anyone got the answer? नहीं रे आर्या और नहीं है. This is an integer question. So the idea is this. I'll tell you. You give it a try. So you have an infinitely long line charge rate, and you kept a plate. So the first idea is to like, okay, why can't I integrate this? That becomes a little difficult. So think from this perspective. Imagine you have a cylinder, right? A long cylinder, and you have an infinite line charge passing through the center. Now try to see the question from this perspective. So this rectangle which you're looking at here, that rectangle is actually something like this. It would look something of this sort, isn't it? I'm not drawing it properly, but that rectangle would be, how do I draw this? I'll just make it big. So that rectangle would be like this. And my diagrams are so hopeless. I give up. So if you look at the side view, right, it would look like a basically a chord here, and you can see the rectangle there. I hope that that's clear. That you can see the rectangle there. And then we are going to make an argument. Now look at the front view. If I look at from the side view, this red line will look like a point. This rectangle will look like a chord. And can I say this way? Every line that passes through this rectangle will pass through the curved surface, which is this one. Are you sure with that? So I need not find the flux on the rectangle. If I can find the flux on this red surface here, the curved surface, that will be the flux in the rectangle. Is that argument making sense, everyone? Now can you try? I'll give you a minute more. Right, Samya. नहीं Aditi. I hope that logic was clear. Since the number of lines are same, the flux passing through that curved surface and the flux passing through the rectangle are same. You just need to find this angle theta here. Because for 360 degrees, the flux is lambda L by epsilon. So for this theta angle, what is the flux? बस हो गया. It's a unitary method. And that's why they gave you these angles and sides and everything. You can find the angles from there. नहीं रे यार यहाँ अच्छा angles आएगा. देखो, from this line charge here, if you drop a perpendicular, what is this distances? Look at this thing. This is the circle. This was there. This was the chord. What are the lengths given? That is A, L, and root 3 by 2. This is root 3 A by 2. This was A by 2, and this was A by 2. And you can clearly see this angle is 30 and 30. This is 60 degrees total. They are done. So for full cylinder, the flux will be the total charge lambda L by epsilon. Now for this 60 degrees, the flux will be what, 60 by 360 into lambda L by epsilon, which is lambda L by 6 epsilon. And then we are going to argue flux through the rectangle must be equal to the flux through the curved part, since the number of lines are same. So there is no need to integrate. And the answer is lambda L by 6 epsilon. Clear with this? Is that clear, everyone? Got the logic behind it? It's difficult to figure it out, but then you know what? When you see these numbers now, this is the trick actually. When you see root 3 by 2 and when you see a, you should know boss is the equilateral triangle. That would give you an idea. This looks like a equilateral triangle and this is the height. It clicks normally. So they're not expecting you to integrate the whole thing. Integration would be a mess. Can be done, but it will be a mess. But any doubts on this? All clear with this? Great. Let's see one more. Then now you're getting hang of this stuff. Yeah, we can keep playing. We can keep calculating fluxes and all. But let's do something even better. We have a square plate with a charged square plate. Uniformly charged square plate. Sigma is your surface charge density. Exactly on top of this from the center, we kept a charge plus q at a height a by 2. And this side is a. A charge plus q is above the plane at a height of a by 2. Now, since both are positive, they will repel each other. Find the force between them. So we have a square plate. On top of a square plate at a height of a by 2, you kept a charge plus q. Since the positive charge and the plate have like charges, they will repel each other. Find the force between them. Let's see how will you handle this. Q a square by 6 epsilon. Q a square. Nere. Think for a minute. This is a little weird. Actually, first time when I did this thing also, that was long back, 7, 8 years back, I guess. It took me time to. I was doing all integration and everything. It doesn't work. There's no need to integrate or nothing. Q by near area. What was the logic also? That is flux per unit perpendicular area. Here the lines are going at an angle. कुछ भी नहीं कर सकते. Chalo, listen. I'll show you one. This thing, right? The idea was this. When I saw this question for the first time, I don't know where I saw this, but I was trying integration and everything. And then after 10 minutes, right, I said, okay, Ruko, this was given an exam, right? First of all, integration, right? This is not a max class. So they're not expecting you to integrate. So this is what my thought process was. And next thing, they're expecting you to solve this in 3 minutes. I said, ठीक है. So matlab, there must be a way to do this in 3 to 4 minutes. I said, great. Then I saw the numbers. I said, a by 2 tha or ye tha. This is exactly the center of a cube, isn't it? This is the center of a cube. I said, great. So there is some kind of a symmetry. That means I can find the flux through the plate. Q by 6 epsilon. Abhi calculate kiya tha humne. If I put 5 more plates, it will become a full cube. Then each face will have Q by 6 epsilon. Itna tak aa gaya tha. Now at this point, I started thinking that means somehow flux is related to the force. I don't know how yet. Once I figured out till there, right, then the remaining things fell in place. Then I solved it in 2-3 minutes. Now it's all random. Like, pata nahi, why did I start thinking that way? But my idea was that, like, you gave such a good number, so there should be something related to the flux. Maybe that's what you call as thinking. So you try to relate everything and things fall in place. So listen to this process. Now, if you take any random flat surface, okay, so we will take a random flat charged sheet. And let's say you put your point charge Q here. So the argument was this. So from here, consider a small piece here. So on this small piece, you will have an electric field at some random angle. This would be theta. So theta is changing everywhere. So on this small piece, the forces, if you see, you will have two components of force. This will be dfx and this will be dfy. Right? And the net force will be df in this direction. And the net force, df, will be simply, right, the field, which is E, which I don't know, into dq. And dq is nothing but E into sigma into dA. This is the force acting on this. Now, if you look in the vertical directions, so dfy is nothing but df cos theta. That would be E into sigma dA cos theta. I got till here. Then when I saw that, I said, like, I know this. Now, if you integrate integral dfy and you bring sigma outside, this becomes integral EdA cos theta. And dfy is the net vertical force, Fy, in the vertical direction. This is sigma, and EdA cos theta is nothing but integral E dot dA. And integral E dot dA is nothing but flux. That's a very good result to remember. So the force between the vertical force, okay, we cannot calculate Fx here. So Fx cannot be found. If there's a horizontal component, we cannot calculate it. But for symmetrical objects, Fx will cancel out. For symmetrical shapes, Fx would be 0. So this is your result, which you can remember. The force on a plate will be sigma of the plate into the flux due to the charge on the plate. There, that's your formula, everyone. There we derived it. So the vertical component of force would be sigma into flux. Making sense? Remember, valid only for flat surfaces. If it is a curved surface, it doesn't work. Once you got that, your job's done. And that is the reason that a by 2 is given. If it is a by 4, you can't solve this problem. Other than a by 2, you give any number, I can't do this problem. It doesn't work because you can't calculate the flux. The concept is still right. You can't solve it. So now we will argue plus q. This is a by 2. We can keep 5 more plates. So flux through the plate will be 1/6 of the total. So 1/6 of q by epsilon. Oh yeah, therefore force will be sigma into flux through the plate. Sigma q by 6 epsilon. Easy. Once you know the result, it looks easy. But problem क्या होता है ना आर्या? People keep saying solid angle, they really don't know what they're talking about. Solid angle is defined as the surface area by 4 pi. And how will you calculate the surface area? By integration. So if you have to integrate, वो formula तो वही आएगा ना, which is 2 pi r square into 1 minus cos theta. Remember that? So end of the day, you are integrating anyway. तो solid angle क्यों लेके आना क्यों? It's really not helping you much. That's the thing. Nothing much. Like I didn't want to introduce one more weird concept like unless you get confused. If you can handle it, then it is fine. All clear with this? Understood how we did this? All sure. Now the same way you can play with this also. Now you'll be able to do this. So if you have a disk who is sigma, and on the axial line, if you put a point charge q, making an angle theta, find the force between them. Don't you guys remember the flux due to a disk? किया था हमने last time, याद है? What is the flux passing through a disk q by 2 epsilon 1 minus cos theta? So the force will be q sigma into flux through the disk, which is sigma into q by 2 epsilon 1 minus cos theta. That's your force. Now, if you can play around a little, due to the disk, so the force on the charge q will also be the same. Newton's third law. Force on charge q will be q into the field due to the disk. So you will get the field due to the disk is sigma by 2 epsilon 1 minus cos theta. Do you guys remember this formula? This thing we got it from the integration in electrostatics. And that was the reason when I was teaching you flux, na, some of you felt like अरे हमने ये question कहीं पे देखा था. You can actually find field that way. Are you clear with this? Let's see one more. Any doubts on this? Like, yeah, that was the main idea there. Once you know the flux, it becomes easy to find the force there. Again, you can't find for everything, but some shapes you can. This is another good one. And this we have seen in radiation heat transfer. We have a hemisphere. The disk is having a positive charge, sigma. And this hemisphere has charge plus q. Find the force between the hemisphere and the disk. This is a hemisphere with a charged disk. Radius r. Find force between the disk and the hemisphere. Because both are positive, they'll repel each other. Hollow hemisphere. Let's see how you handle this. Think. Okay, let's see. Anyone got it? Sigma भाई नहीं रहे हमें बहुत अच्छा आंसर आएगा. You guys forgot. Like I said, the idea for this thing is in heat transfer. ये क्वेश्चन याद है? An hemisphere is covered with a disk at the bottom. The disk is maintained at T naught. Find the temperature of the hemisphere. And then we made some argument like this. We said, look at the top surface here. The view factor basically. Only 90 degrees will reach here. So we can do some similar argument here also. See. First, let's be very clear. What is the force on a disk? The force on the disk is sigma into flux due to the hemisphere on the disk. Remember, this formula can be used only on the flat surfaces. Don't use this on the curved surfaces. Matlab, you cannot say force on the hemisphere is sigma into flux due to the disk. That would be wrong. I hope you're clear with that because we derived this only for flat surfaces. It doesn't work for curved surfaces. I tried. You won't get it. You won't get that EDA cos theta flux का term नहीं आता है. Great. Then what is the argument? This is the argument there. We will say take a small charge dq and look at here something nice you will see. If you join this dq to the two corners, this will always form 90 degrees. Agreed? Every point on the hemisphere will make 90 degrees with every diameter on the disk. And now if you take a dq charge, if you look at the field line, the field lines are actually going in all directions. Now in this you are saying I will take 90 degrees. So if you take 90 degrees here, this will be 1/4 of the lines. So due to dq charge, 1/4 of the lines will always pass through the. So these are the kind of questions, right? They're not difficult to solve, but difficult to figure out. Pass through the disk. Therefore, flux will be q by 4 epsilon. Therefore, force will be sigma q by 4 epsilon. Bas, you're done. Is that clear, everyone? Making sense, right? Trishi? Clear with that? Samyak? Param? Anvita? Aditi? Arya? Bolo?
So, like, I didn't get how you wrote the force directly.
Hey, अभी डरा गया ना ये पूरा स्टोरी क्या सुन रहा था
So, nahi, like, how did you use that result? Because we derived it for a point charge.
ठीक है ना. So ऐसा कर लो. This is the force between the point charge dq and the disk, vertical direction में. And when you
Okay.
integrate it, won't you get the sum of all the forces? तो integral dq हो जाएगा ना वो. So the
Oh,
force due to
because
the
it's
small
subtending
charge will be
90,
sigma
it should be
dq by.
4.
ऐसा होगा
Okay.
ना force, agreed?
Yeah.
Integrate करेगा तो dq क्यों हो जाएगा?
Yeah. But
Because every point, doesn't matter which point you take, won't they all subtend 90 degrees?
yes, sir.
So it works. Basically, then we can say everyone is contributing 1/4 of their own flux. So everyone has same vertical component. You just add them up. Vertical components, horizontal करेंगे नहीं. So you'll get horizontal will anyway cancel out because of symmetry. All clear with this? I hope you can see, right, how we are playing with the flux. We started the whole story with flux is equal to number of lines passing through an area. Then we said flux is integral E dot dA. Then we proved flux is q by epsilon for a closed surface. But I think if you actually see, we did only these three things. And after that, we just kept on adding that, this, and we started playing around with this, all this stuff. Great. So yeah, now you guys are good enough with flux calculations. Like you can handle stuff. And I think you understood like why I said this chapter is a little different. You don't have a lot of calculations and equations. It's all about arguments. And that's what makes this thing little tough if you don't really understand. So make sure to revise the whole thing. Well, let's say something a little more mathematical. Let's say we have an electric field in the region EXI cap. This is another good model. 2yj cap plus 3zk cap. So you have a field which is changing. Find the flux in a small cuboid of sides dx, dy, and dz. So consider a very small cuboid. What will be the flux in that small cuboid because of this electric field? Find the charge enclosed. I'll show you a picture how it would look in a radius r. In a sphere of radius r whose center is at the origin. This is what I'm asking. So x, y, and z. So someone is asking you to construct a small cuboid. Again, I'm drawing a big one, but technically it should be very small. Whose dimensions are, this would be dx, this would be dy, and this is your dz. So chota cuboid, a very small cuboid. What is the flux in this small cuboid because of this field? And remember, the field is not same. So think, let's see how will you do then. This would be a good advanced more than one choice question. It won't be zero, na? Field uniform nahi hai yaar, yeah. Think about it. With x, field is increasing, right? The number of lines on the left and the number of lines on the right will not be same. As x increases, you get more and more field lines. मतलब बीच में कहीं पे charge है, they're generating more field lines. Let's see. Right, Aditi? Right, Samyak? नहीं आ रहा. We just got dB. उससे क्या आएगा? Okay, listen. So let's consider our small cube. I'll just draw it big. It's actually cuboid, huh? Not a cube. So this was your dx, this was your dz, and this was your dy. So look at this surface here. If you look at this surface here, the field here, let the field be E, and let the field be here E plus dE. Let's take it as X. So that means the field in the X direction will create a flux on the area dx dy. So we are creating on this. So here the area ka term will be dy and dz. Is that making sense? For the horizontal direction, y and z is the perpendicular. Therefore, the flux due to Ex, so we are taking due to each component, will be Ex plus Dex. So we are assuming the field has changed by a small amount into dx, dy, dz. This is the field which is leaving minus Ex into dy, dz. This is the field which is entering. So the net flux will be dex, dy, and dz. The same way I can argue, and I can also do it for Ey. You can see now this will be dEy. The area will be the perpendicular ones, dx, dz. Similarly, the flux due to Ez will be the same thing, dEz, and the area will be dx, dy. Is this making sense? So each component of field will create flux differently. So this is the general formula for a flux. The flux for a cuboid would be dex, dy, dz plus dey, dx, dz plus dez, dx, dy. This is the flux passing through the cuboid. This is a general formula, everyone. I didn't prove this for any particular field. I proved it for any random field. Clear with this? And now in our question, it is given the electric field was xi cap plus 2yj cap plus 3zk cap. So basically, this is your Ex, this is your Ey, this is your Ez. That's the coefficients. You wanted Dex, which is dx. Dey is 2dy. Dez is 3dz. Substitute. You get flux is equal to dx, dy, dz. 2 dx, dy, dz. 3 dx, dy, dz. Which is simply 6 times dx, dy, dz. Which can be written as flux through a small cuboid is nothing but 6 into dv. dv is your volume. And that will give you the answer for the B part also. Now you want the flux through a sphere. So flux through a sphere, you can divide the sphere into chota small cubes. That will be 6 into dv. That will be 6 into volume of the sphere. So the first and the second are related. If you don't get the first one, you won't get the second one. That will be 6 into 4 by 3 pi r cube. What are you asking? You are asking for the charge enclosed. But I know flux is nothing but charge enclosed by epsilon. This is what we proved before. So that you got the answer. So Q would be, how much is that? 24, that's 8 by epsilon r cube. So this much charge was there in the cube. But please have a look at this. All got this idea there? This is not an easy one. Huh? This is a really good one. This would be proper advanced stuff. Could be more than one choice or paragraph. It's too small to be a paragraph. It's too tough to be a single choice question. So yeah, it's a good one. All clear with this? So we proved actually the flux in a particular because this is lucky, huh? यहाँ पे ex ey ez came in such a way you got dx dy by dz. If your ex ey are like x square to y cube and all, you won't get such a beautiful equation. You will end up with 2x dx dy dz, something like 6y square dx dy dz. So you won't get such a good number. It will be pretty messed up. This question is special. The numbers are framed in such a way you'll get a good 6 into dv. So this was a special case. It won't happen every time. Yeah, but this thing in the red one is a general case for any kind of field, so it works. All clear with this? Take a break, come back in 5 minutes, we'll continue from here. Come back by 9:46. Any doubt so far? Chalo, come back in 5 minutes then. Yeah, comes on everyone. So great. So we have calculated flux and all this stuff and great, but exactly what are we using this for? We did find force and stuff, but the primary use was this. Now let's actually define what is Gauss law. Technically, we have proved everything. So first thing, we will define something called a Gaussian surface. So a Gaussian surface is an imaginary closed surface. Remember, that is the first thing. It is imaginary. So you are just imagining, okay, there is a closed surface. An imaginary closed surface on which electric flux is calculated. So if you take, so the main words are that it is a closed surface. If you calculate electric flux on a closed surface, it's called a Gaussian surface. That's a definition. Straightforward. What is Gauss law? The Gauss law says flux over a Gaussian surface is 1 by epsilon times the charge enclosed. And this is we already proved it. So the thing was this, Gauss law came first, then came Coulomb's law. Coulomb's law is actually more powerful than Gauss law. But then again, just like, if you remember pressure and buoyant force came first, then came pressure. So Gauss law has its own advantages. So the flux is given by integral. We put a circle ka symbol here. I'll tell you what it means. E dot dA. Others do keep your cams on. Is equal to Q enclosed by epsilon. Yeah, that's a mathematical symbol there. So for an integral, if you put a circle here, this is called a closed integral. I don't know whether they did this in max for you already. So when you see that circle, it means you're integrating over a closed surface. So when you integrate flux for a disk, you don't put that circle there because it's not a closed surface. This is an integral over a closed surface. There, everyone. So yeah, technically this is your Gauss law, which you already know, which we proved in the last class, if you see, using Coulomb's law. All clear with this? Going ahead. So if you have some surface like this is Q1, this is minus Q2, this is Q3, and this is Q4. So when you write the flux is integral E dot dA is equal to Q enclosed by epsilon. So this E is actually of whom? This is the electric field due to everyone. This is the electric field due to all charges inside and outside. But what is Q enclosed? This is only the charges inside. Why is that happening? Like, why are you taking full field if you're not going to consider those charges inside? Let's see what it means. So if E is due to all charges, I can split this into integral E bar dot dA can be written as integral E1 bar plus E2 bar plus E3 bar plus E4 bar dot dA. This is E1 dot dA, E2 dot dA, E3 dot dA plus E4 dot dA. What is this? This is the flux due to each charge. But we know this guy is 0 and this guy is 0. Phi is 0 because we proved it. If you remember, the flux due to a charges outside will be 0. Since outside charges do not generate any flux. So that is a catch. E is not 0, but integral E dot dA is 0. So that is the reason, if you take, technically speaking, this E should be E1 plus E2, isn't it? But even if you take E3 and E4, it won't create a problem because you're simply adding zeros. Is that making sense, everyone? Do not contribute to flux. And where you have seen this? There, this is what we proved, isn't it? Integral E dot dA is 0, the total flux. If you have a charge outside a Gaussian surface, it's not going to create any flux. If it's not going to create any flux, you can just add it up. It's like you're adding 1 plus 0. It's not going to create any problem. So technically speaking, this E bar can be anything. So E bar can be E1 plus E2. That is right. It can be also E1 plus E2 plus E3. That is also right because that E3 will be anyway 0 there, integral way. It could also be E1 plus E2 plus E3 plus E4. It's like you're simply adding zeros, so it really won't matter. All clear with this? Great. So what are we exactly going to use the Gauss law for? Listen carefully. I'll show you one or two examples and then we'll do more on this. So this is important. So Gauss law ka primary uses this. So Gauss law is useful to find electric field for symmetrical charge distributions. You cannot find for everything, but for symmetrical things you can find. To find electric field. Due to symmetrical charge distributions. So listen carefully, everyone. I'll show you a few examples. This would be the important part. So they do frame questions on this a lot. And there are certain shapes which you cannot find using Coulomb's law. So let's take the first example, an infinite line charge. And I hope everyone already remembers the formula for an infinite line charge. Yeah, 2k lambda by r, right? So that was the formula. Infinite line charge, this is plus lambda. So you want to find the field due to an infinite line charge. Great. Step 1. Choose a symmetrical Gaussian surface. So you have to choose a symmetrical surface. What do you mean by symmetry? Every point on the surface must look identical to the line charge. Choose a symmetrical Gaussian surface. Again, what is Gaussian? Again, don't get confused. Gaussian means simply a closed surface on which you're going to calculate flux. Okay, so how can I take a symmetrical surface here? Can I take a sphere? Now see, be careful here. Sphere is symmetry, but is every point on the sphere identical? Aren't there different distances? So sphere is a bad idea. Can I take a cube? Yeah, not exactly again, because if the diagonal is longer, the sides are smaller. Again, this is not symmetrical. So if you think about it, you will notice a cylinder is the symmetrical shape, isn't it? So for a line charge, a cylinder, every point on the cylinder is equidistant. Are you sure with this? That is the first thing. So consider a closed surface. So you have to close on the top, you have to close at the bottom. Perfect. Now, because it's an infinite line charge, we know the field will be away from the center. So this is E, this is E. So here also it will be E, and here also E and E and E. Great. If you look at the area vector, this will be dA. This will be dA. So this perpendicular, there will be no flux on these disks. Perfect. Step 2, calculate the flux. And use flux is equal to Q enclosed by epsilon. That's it. The main idea was that. So what is the flux in this problem? So flux will be E into 2 pi RL because the curved surface, there is no flux on the disks. This should be equal to Q by epsilon. That is the charge enclosed in the cylinder. How much charge is enclosed? Lambda into L. Therefore, we get E is equal to lambda by 2 pi R epsilon, which is nothing but 2k lambda by R. Clear with this? If you remember how we derived this result, we did a big integration in electrostatics. There. We actually found the value for a finite rod, and then we said theta 1, theta 2, 90, and then we got the result. So we can actually get this result without all that integration very easily. But the drawback is what? If I give a finite rod, Gauss law is useless because there is no symmetry. So Gauss law is powerful when there is a symmetry. Are you all clear with this? Let me take one more example. Solid sphere. Uniformly charged solid sphere. So we got a solid sphere, charges plus q, radius r, charges everywhere. Okay, step 1, consider a Gaussian surface. So we will take for r less than equal to r for the inside points. So consider a Gaussian surface. So we will consider a Gaussian surface inside of distance r. So integral E dot dA, this is your flux is equal to Q by epsilon. So you can clearly see here by symmetry, the field will be radial. The area vector also will be radial. E bar will be always parallel to dA. This would be E, and the area of this surface is 4 pi r square. So you want to find the charge inside this red sphere, right? This Q is a charge up to small r. That would be rho charge density into 4 by 3 pi small r cube. But what is rho? Rho is nothing but total charge by volume 4 by 3 pi capital R cube. So this would be 1 by 4 pi r square. Epsilon, rho will be q by 4 by 3 pi r cube. That's q r cube by r cube. You end up with q small r by 4 pi epsilon r cube. So this is k q small r by r cube. Do you guys remember this formula? The field inside a solid sphere? Isn't that the formula we got? So there, this was the proof actually. This is the field inside a solid sphere. What about outside? If we take r greater than r, then we will consider a Gaussian surface outside. Here it is easy because all the charge is inside. Again, same story, flux is equal to integral E dot dA is equal to Q by epsilon. This will be E into 4 pi r square. Here Q is the total charge by epsilon. So we get E is equal to KQ by r square. There, this is the field outside. Is this making sense, everyone? So that's it. This is how you can use Gauss law to find field due to symmetrical distributions. Main word है symmetry होना चाहिए. If you take some random shape and random distribution, we cannot use Gauss law. Why you need symmetry? Because if it is symmetry, then I can say E dot dA is same and E will come out of the integral. If there is no symmetry, वो E integral से बाहर नहीं आएगा, and then you can't solve. All clear with this? Now I'll give you a few shapes which we didn't do in electrostatics. So you guys give it a try and then I'll show you. The first shape is an infinite hollow cylinder. So we have an infinite hollow cylinder. The charge density is sigma. So this whole surface has charge. The radius is capital R. Find the field inside and outside. Find the field as function of R. R is the distance from center. Again, remember the process. Step one, let's take inside. Consider a Gaussian surface, right? And then find the flux is equal to Q by epsilon. Take a minute or two. I'll show you one and then I'll ask you one more. But you give it a try. If you remember, there is no formula for this in electrostatics. We never derived. It's difficult also. But Gauss law will make it look so easy. Find the field inside and outside the hollow cylinder. Yeah, I told you. Get the outside part also. Yeah, inside is zero. That's right. Get the outside part also. Try. Okay, let's see. Listen, I'll show you one. Same story. Step one, consider a point inside and outside. That's how you always start these kind of things. Because you can clearly see the inside and outside two different regions. How will you take a Gaussian surface? A cylinder. Consider a cylinder of length L and radius small r. We can clearly see the field for the cylinder is radial. The area vector is also dA. This is the whole reason why you should take a symmetrical shape. So for r less than r, the flux will be E into the surface area, which is 2 pi r into L. This should be Q enclosed by epsilon. But I don't see any charge inside because it is hollow. This is zero. Therefore, E is zero. There is no field inside a hollow cylinder. Next thing, for r greater than r, meaning now you're considering a Gaussian surface, much bigger one, the black one. I can just draw a new picture if you want. Maybe we can consider here. So I can consider a Gaussian surface here. So for the black one, the flux will be same thing. So I'm considering this also to be some radius r. Remember, r is just a variable. This would be E into 2 pi r L. Now, what is the charge here? Inside this black cylinder, this is all the charge that you have, which is on the cylinder, which is sigma into 2 pi capital R into L. Is that making sense, everyone? If you take a cylinder, the bigger one, all the charge inside, right, will be this red one. That much charge is inside. That would be E is equal to sigma capital R. L will cancel, 2 pi will cancel, epsilon small r. So it's actually 1 by r function there. So if you actually try to plot a graph for field versus r graph, the field will be 0, then it would rise and then drop. It looks like hollow shell ka result. All clear with this? This is a field inside a hollow cylinder. We don't have this result in electrostatics. You should know how to do this. These questions itself will be a proper mains level questions. Any doubts on this? No. The second shape. Infinite solid cylinder. Rho is the volume charge density. Find the field inside and outside. Meaning there's a charge everywhere. There, give it a try. You do get these questions, especially they can ask you plot the graph. Which of the following is a graph? Hmm. Right, Samir. Get the outside also. That looks right. Get the outside one also. Yeah, 2 r square by r square. By r square नहीं आएगा रे पर. That looks right over here. Okay, let's see. Same story. Let's take for r less than r. Consider a Gaussian surface inside. R less than r is inside. Length L. So same idea there. So flux will be E into the surface area. Remember, it will be only on the curved surface because here the area and the field are perpendicular. I have seen that already. What is the charge inside? So this is Q by epsilon. So this Q is the charge inside that green cylinder. That is the charge enclosed. How much is that? That is simply rho into volume. What is the volume of a cylinder? Pi r square L. Dump it there and then you're done. So this will be E into 2 pi r L is rho into pi r square L by epsilon. We get E is equal to rho r by 2 epsilon. Please check. Then when you take for r greater than r, now we are taking a cylinder like till here. Now we have to find all the charge inside this black thing, which is nothing but the solid cylinder only. Interestingly, if you see, the left hand side will always be the same, which is E into 2 pi RL. And what is the charge? Rho into, now be careful here, that there is a charge only till capital R, pi r square by L epsilon. That would be rho r square by 2 epsilon small r. It's again 1 by r function there. So do have a look at this. So if I ask you to plot a graph, E versus R, the graph would look like this. It's a linearly increasing function and decrease. Again, looks like a solid sphere ka result. It's not the same though. It's 1 by R. All clear with this? You're getting how to use these things? You should definitely try this again on your own once more. Any doubts on this? Clear, na, Aditi? Ishman? Clear with this? Srihari? Vanshika? Kanchika? Clear? Yashvi? Clear? Shriyansh? Shreyan? Okay, let's see one more then. This is a good one. We have a solid sphere. The charge density rho is rho naught r power n, meaning your charge density is not uniform. It is increasing as you go outside. R is the distance from center. And n is not equal to -3. You will see why. Find the field as function of r. Just to give a little idea, think of like this. For example, if n is 1 or something, if r is 0, there is no charge in the center. If you go little outside, then there is a small positive charge. When you look at how this sphere is constructed, if you go little more outside, you have little more charge. Means as you go outside, the charge is becoming more and more. If you go little more outside, you get even more charge. So this is a sphere. So if you see technically, even though the charge is changing, it is still uniform radially. And on the outermost surface, we have maximum charge. I think you got the idea. So someone constructed a sphere whose charge is increasing as you go out. The charge is just increasing. Find the field. Quite an important question. Good result. It has been asked multiple times. Not this one. In the exam, they asked for rho into r power 1. We are doing for n, so you will get for any case. Let's see how we'll do this. How do we do this? It's a little lengthy. Take a minute or two. Think about it. You have to integrate. One thing is clear. How do you choose an element? That you must have figured out by now. We consider an element inside, then we have to find the charge inside of this, and then we'll take an element outside, then we'll find the charge, and we have to do it. Rho r bar, right, Samyak, that you got. Ovya rho r bar n plus 1. Yeah, that looks right. Get the outside part also. Right, Ovya, right, Samyak. It's, anyone else? Rho 4 pi 4 नहीं आएगा ना अच्छा 4 pi नहीं आएगा I think you forgot to cancel it. Let's see. Yeah. So listen carefully here. It involves a bit of an integration here. So consider a Gaussian surface here at a distance r. Now the biggest problem we have, first thing is we have to find the charge inside this green sphere. So let's start from there even before starting the problem. So if I take this green sphere of radius r, so even within this chota green sphere, the charge is changing everywhere. So at a distance x from here, consider a thin shell. By now, I hope you understood, right? When you see a solid sphere, this is how we take an element. So the charge on that thin shell, the Q on a thin shell, is simply the charge density rho into the volume dV. The rho here is rho naught into r power n. dV, it's rex power n, and dV is nothing but 4 pi x square surface area into thickness. So this is the charge on a thin shell. So if you want the charge Q, this is a Q, is the charge up to small r. Will be integral rho naught 4 pi x power n plus 2 dx. This will go from 0 to r. This is rho naught 4 pi r power n plus 3 by n plus 3. I think now you understand why I said n is not minus 3. So what is this? This is the charge in the green sphere. This is the first thing you need to know even before jumping ahead. Great. So we have one result here. What is the total charge? The Q total will be when small r becomes equal to capital R. That also we'll need later on. So that is 4 pi into r power n plus 3 by n plus 3. This is the total charge on the sphere. The Q is simply the charge up to small r. Any doubts with this page? So we know the charge in that chota green sphere and we know the total charge, I think. Once we know these two things, my job becomes pretty easy. Then we will say same story. Consider r less than equal to r. Flux will be here integral E dot dA. That will be charge enclosed by epsilon. This is A. For a sphere, the area is 4 pi r square. The charge enclosed, just now we proved this is the value there. Rho naught 4 pi r power n plus 3 by n plus 3 epsilon. 4 pi will cancel, r square will cancel. You end up with rho naught into r power n plus 1 by n plus 3 epsilon. There. It's a pretty good result though. That's your field inside. For r greater than r, same story. Flux will be E into 4 pi r square, meaning you're taking a sphere outside. This should be the total charge, which is because you're enclosing the whole sphere. This is q total by epsilon. What is q total? We have calculated that also. Substitute there. Rho naught 4 by r power n plus 3 by n plus 3. There you got the field from here also. So the main idea was to calculate the charges. That's where people find it little difficult. There, please have a look at the steps. Is the charge part clear, everyone? At a distance small r, I took a small green sphere, but within this green sphere, the charge is changing everywhere. So I said within the green sphere, take a thin red color shell. So chota red shell में this much charge you have. If you add all these charges, you'll get the charge on the green sphere. If you take small r is equal to capital R, that means your green sphere has become till this part. That means you're calculating the total charge. So once you got the charges, you're done. You can put it there and finish it off. These things are little lengthy and it involves working. And also remember, this is all there for HSC board exams. Maybe not exactly this stuff, but they do have derivations for solid sphere, infinite sheet, and all. The board exams they do ask you, so you have to write more statements there. So yeah, this is a good question. You should definitely give it a try again. Let's do one last one. We have an infinite slab. Rho is the volume density and the thickness is d. Next class will be quite theoretical, huh? So please be fresh and gum. Don't be tired. There will be a lot of statements and arguments and everything to prove stuff. Like quite an important class in the next thing. If you got that, I think Gauss law, that is a major thing. You'll understand most of it. So look at this thing here. I'll just give you some more variables here. So this is your infinite sheet side view. This is the central line. So the distance x is measured from the central line. Find the field as function of x, where if you take x is less than d by 2, means it is inside the slab. X greater than d by 2, you're outside the slab. So find the field as function of x. This is d by 2 and this is d by 2. I hope you can see the side view. You have a thick slab of thickness d. If you take x is equal to 0 as the central line, so you have to find the field inside and outside. Let's go. Finish off. Last one for the day. How do we handle this? Rho x by epsilon, rho d by epsilon. एक 2 आएगा भैया, चेक कर लेना. Again, listen, meaning it's all about choosing an element properly. Let's take the side view, okay? I'll make it very thick so you can see it clearly. So first we want to do so this is the central line. You're taking for a case where x is less than d by 2. So let's take a case where x is less than d by 2 and less than minus d by 2. So let's take both the sides. So we will consider a Gaussian surface like this. So those sides, na, you have to take both the sides symmetrical. So this is x and this is x. So this is the area and this is the area. Now we can clearly see this is the field, this is the area vector. This is the field, this is the area vector. Agreed, the field is opposite, but area vector is also opposite. So the flux will be 2 times EA. So that would be like E into A plus the field is backward minus E. The area is also backward minus A. That's your total flux, which should be Q by epsilon. So 2EA, what is Q? Q is a charge inside the red cylinder, which is rho into area. The cylinder ka thickness is 2x by epsilon. Be careful, x is measured from the center. So you should take x on both the sides. So this would give you E is equal to rho x by epsilon. It's a linear function. Meaning inside the thick sheet, the field will increase linearly. Now, if you take for x greater than d by 2, so meaning I'm considering a cylinder passing through the whole thing. This is E, this is A, this is E, and this is A. Same story. Here also the flux will be 2 times EA. But this time the charge will be rho into A into, remember, the thickness is only up to D. So that will be rho A D epsilon. You end up with E is equal to rho D by 2 epsilon. Got the two? You have to consider both the sides. If you say, no, I will not consider both the sides, fair enough. That means your cylinder is starting from here, isn't it? Then you should take only D by 2, na? Rho into D by 2. So either way, you would always get to there. So if you try to plot a graph for this, you will get a pretty interesting graph here. So the function will increase linearly, and then it is becoming constant. This is happening at D by 2. And reverse may, if you see, on the left-hand side, the direction has changed. So field is decreasing. It is on the left-hand side, becomes constant. The graph is a nice one. This is how the graph will look for the infinite sheet. The negative sign indicates the direction got reversed. Are you clear with this? And if you guys remember, right, we already calculated for infinite sheet before. So yeah, we can do the same thing now. So if you take an infinite charge sheet, so it's basically a slab whose thickness is almost negligible. If you have an infinite charge sheet, if you have plus sigma, you have minus sigma. The plus sigma will create a field of sigma by 2 epsilon. We did this before. The field will be away from the sheet. If you have a negative charge sheet, the field will be towards the sheet. Again, the magnitude is sigma by 2 epsilon. So a sheet will generate a field of sigma by 2 epsilon. Now, sometimes they'll use the word infinite plate. So the difference between a plate and a plate has a thickness. So that means it can be treated as two sheets. So an infinite plate will have two surfaces. So here the field will be sigma by epsilon and sigma by epsilon. So just be careful with that wording there. So are you talking about a sheet or a plate? In a sheet, you know what happens when you look from the right side or the left side, you're looking at the same molecule. The sheet is so thin. That so this is how we use Gauss law to find field due to different shapes, especially symmetrical shapes. Clear with this? That's one of the more practical applications. So next class when we catch up, right, we are going to do something called field inside a conductor. Then we are going to see what happens if a conductor has cavity, how will the fields distribute. So we have some really good theoretical stuff there. It'll be quite an important class. Yeah, and that would be there. And I think we'll take another 2 classes. We will wrap up this chapter. It's not a big thing. So after that, we'll start off with capacitors. So okay, with that, we'll wrap up for the day. And especially, we did a lot of symmetrical questions today. So please spend some time, take a rough paper, just resolve them. See, that is how you revise the notes. Don't flip the pages like a novel. You will not learn anything, right? So if you can see, right, we did the question. You have a question. Take a rough paper, try to solve. Since you learned it today, don't you think you should be able to do it tomorrow? But nahi hota hai, trust me. 50% of the time, it won't click only. And the reason is because it takes time to absorb. You guys are under the impression, I listen to it, so I know. Nahi hota aisa. It's like watching a YouTube channel and thinking I know how to cook. It's a big joke. The same way, teacher taught you, you think you know. That's not going to happen. You have to go home, you have to resolve on your own, and then it becomes yours. So please do that. So Thursday when we catch up, we'll continue from here. And do remember there's a test online till Friday, so make sure to give it. So any doubts, anything else, please stay back, or else you're free to leave. I'll see you guys again on Thursday, same time. So take care, stay safe.